Next time you happen to walk past a mirror, stop for a second. Lean in close, closer than you normally would, and take a really good look at your eyes. Whether your eyes are deep brown, icy blue, shifting hazel, or bright green, they are indeed one of the most intriguing biological mysteries humans have today. We are a spectacularly colorful species today, but it absolutely was not always this way. If you could build a time machine and go back 300,000 years, then walk among our earliest human ancestors, you would notice something remarkably uniform. Everyone, literally every person you saw without exception, would be staring back at you with deep, dark brown eyes. For the vast, overwhelming majority of the human story, having any eye color other than brown wasn't just rare, it was biologically non-existent. There were no ancient blue-eyed hunter-gatherers scanning the horizon, no green-eyed cave painters in the Paleolithic eras of Africa. We were a strictly brown-eyed species. What changed over time to turn a once uniform, brown-eyed species into a worldwide population that now displays a full kaleidoscope of different iris colors? The answer is a long story, involving ancient migrations, mutant genes, sexual selection, and a delicate dance with the sun. To really understand why your eyes look the way they do right now, we have to travel back to the cradle of humanity. Picture yourself in the sun-drenched savannas of East Africa, roughly 2 million years ago. This is the stomping ground of Homo erectus, one of our most successful and longest-living ancient ancestors. Life out here was brutally unforgiving, and the absolute dictator of this environment was the sun. It beat down relentlessly, flooding the plains with heat and blinding light. It also delivered massive, potentially lethal doses of ultraviolet radiation. In this harsh landscape, survival wasn't about being the strongest or the fastest. It was about being the best adapted to this endless bombardment of solar energy. This is where melanin steps into the spotlight. You have probably heard of melanin when people talk about skin color, but it is the exact same pigment that dictates eye color. Think of melanin as Mother Nature's microscopic, built-in armor. On a cellular level, melanin is produced by special cells called melanocytes. Its primary job is brilliant. It absorbs and dissipates ultraviolet light before it can damage your DNA. Now, let's look at the anatomy of the eye. The colored part of your eye is called the iris. It is a complex muscular curtain that controls how much light reaches the back of the eye. The iris is made of a few layers, but the most important one for our story is the front layer, called the stroma. In early humans living under the equatorial sun, this stroma was absolutely packed, wall to wall, with dense melanin pigment. When you look at a dark brown eye, you are seeing a heavy layer of protective pigment. It absorbs almost all the light that hits the iris. Very little light bounces back out, which is why the eye looks so dark. And in prehistoric Africa, this wasn't an aesthetic choice. It was mandatory survival gear. The human eye is incredibly sensitive, and prolonged exposure to intense UV radiation without protection leads to a whole host of catastrophic problems. It can burn the cornea, damage the retina, and dramatically accelerate the formation of cataracts, which is a clouding of the eye's lens. Today, if you get a cataract, you can go to a hospital and have a routine surgery to fix it. If you developed a severe cataract on the African savanna 200,000 years ago, you were effectively blind. You couldn't hunt, you couldn't forage, and you certainly couldn't spot a predatory big cat sneaking through the tall grass. A severe eye injury or loss of vision was essentially a death sentence. Therefore, evolution ruthlessly favored individuals with the darkest, most melanin-rich eyes possible. Those heavy brown irises acted like high-grade sunglasses, absorbing the dangerous UV rays and protecting the delicate structures deep inside the eye. The darker your eyes, the better you could see in glaring sunlight, and the less glare you had while tracking prey across the bright plains. Darker eyes also helped keep your vision intact into old age. The genetic instructions for packing the iris with melanin were locked in tight, passed down from generation to generation without fail. It was a perfect, unbroken system. The environment demanded heavy protection, and human biology provided it, flawlessly, for hundreds of thousands of years. But humanity has never been very good at staying in one place. We are an endlessly curious, restless species, with a deep-seated urge to see what lies over the next horizon. And as our ancestors began to push the boundaries of their world, venturing out of the sun-baked cradle of Africa and moving steadily toward entirely new, alien environments. That perfect, unbroken genetic system was about to encounter a problem it had never faced before. The sun was going down, the skies were growing gray, and Mother Nature's built-in sunglasses were about to become a massive liability. As bands of early Homo sapiens began their epic trek out of Africa roughly 60 to 70,000 years ago, they were walking into a completely different world. They pushed north and east, winding their way into the rugged landscapes of Europe and northern Asia. As they climbed higher in latitude, the environment changed drastically. The scorching, relentless equatorial sun was replaced by overcast skies, freezing temperatures, and long, dark, bitterly cold winters, where the sun barely peaked above the horizon. Remember that thick layer of melanin we just talked about? In the African savanna, it was your absolute best friend. But up here, in the dim, frosty twilight of an Ice Age winter, it suddenly became a serious liability. Think about it. It was literally the equivalent of wearing dark, polarized sunglasses in a dimly lit, shadowy room. While heavily pigmented eyes might have slightly reduced visual contrast in the gloomy northern hunting grounds, there was a much bigger, life-threatening crisis brewing in these populations, and it was tied directly to the exact same melanin factory that colored their eyes. The crisis all comes down to vitamin D. Unlike most vitamins, which we simply absorb from the food we eat, vitamin D is actually a hormone that our bodies have to manufacture on their own. But there is a massive catch. To trigger this chemical manufacturing process, our bodies need to be physically struck by ultraviolet B radiation from the sun. And you desperately need vitamin D to survive. Without it, the human body completely loses the ability to absorb calcium from food. Without calcium, bones fail to harden. They become soft, brittle, and weak, a devastating condition known as rickets. If an ancient hunter-gatherer child developed rickets in the frozen north, their legs would literally bend and bow outward under the weight of their own body. In a brutal, prehistoric world where you had to run, hike, and hunt every single day just to stay alive, weak bones were a guaranteed death sentence. In Africa, there was so much intense UV radiation that dark skin and dark eyes were strictly necessary to prevent DNA damage. But in the cloudy, high latitudes of ancient Eurasia, the sun's rays were so weak and filtered that high levels of melanin acted like a heavy lead blanket, completely blocking what little, precious UV radiation was actually available. The heavily pigmented humans migrating into these northern regions were suddenly starving for vitamin D. Evolution had to act fast, and it had to reverse its strategy entirely. Evolution's directive flipped from block the sun at all costs to capture every last ray of sunlight. To pull this off, the body had to strip away the melanin. This brings us to an important piece of our genetic code, the OCA2 gene. Think of the OCA2 gene as the master volume knob controlling how much melanin your body produces. For hundreds of thousands of years, that volume knob was cranked all the way up to a solid 10. It made a protein that worked like a fleet of delivery trucks, constantly moving the raw materials needed to build melanin into the cells. But as human populations settled deeper into the north, genetic mutations began to appear that incrementally turned that volume knob down. The delivery trucks slowed their routes. The melanin factory was put on part-time hours. As a result, their skin lightened, becoming paler and more translucent, so it could absorb the weak northern sunlight and produce the vitamin D they needed. This is where it links back to the eyes you see in the mirror. The body's melanin system is highly interconnected. The OCA2 gene doesn't just control skin pigment, it dictates eye and hair pigment too. As evolutionary pressures furiously dialed back the melanin in the skin for basic survival, the melanin packed into the irises naturally began to thin out as well. The dense, impenetrable dark brown eyes of our ancestors gradually began to lighten, shifting over generations into softer, lighter shades of amber and light brown. However, this general fading effect, this simple turning down of the volume knob, was nowhere near enough to give us the shocking, crystalline blue eyes we see in the world today. For that to happen, a much more dramatic, 1 in a billion genetic accident had to take place. The story of blue eyes wasn't just about waiting for the volume to slowly turn down. We were waiting for someone's genetic code to accidentally, permanently, flip the power switch entirely off. To find that exact moment the switch was flipped, we have to fast forward through tens of thousands of years of human migration, landing right around the end of the last ice age. We are looking at a region somewhere near the northwestern shores of the Black Sea, roughly 6 to 10,000 years ago. Picture a small nomadic tribe or early farming community going about their daily lives. In this specific tribe, a microscopic typo occurred in the DNA of a single human being. It wasn't a violent mutation or a life-threatening disease. It was just a tiny, silent genetic stutter. But that stutter would go on to permanently alter the face of the human race. This brings us to a piece of genetic code called the HERC2 gene. If OCA2 is the body's volume knob for melanin, you can picture HERC2 as the manager on the same chromosome whose job is to carefully turn that knob. They sit right next to each other on chromosome 15, and they usually work in perfect harmony. But in this one specific individual living near the Black Sea, the HERC2 gene experienced a mutation that essentially acted as a highly targeted short circuit. Here is the brilliant part about this mutation. It didn't completely destroy the body's ability to make melanin. If it had shut down the entire factory, that individual would have been born with albinism, lacking pigment in their skin, hair, and eyes entirely. Instead, this specific HERC2 mutation was astonishingly precise. It reached in and shut off the melanin production strictly and exclusively in the iris of the eye. It stripped away the dark pigment that had protected our ancestors on the African savanna for 2 million years, and it scrubbed that pigment out of the eye's front layer. When that baby opened their eyes, rather than the familiar warm brown of their parents and every ancestor before them, they saw the world through irises of startling, piercing blue. Now, prepare yourself for what might be the most mind-bending scientific fact in this entire story. In 2008, a team of researchers at the University of Copenhagen decided to track the genetic history of blue eyes. They examined the DNA of blue-eyed individuals from all over the planet, from blonde-haired Scandinavians in Denmark to dark-haired individuals in Jordan and Turkey. What they found completely floored the scientific community. Every single blue-eyed person they tested had the exact same genetic mutation, sitting in the exact same spot on their DNA. In genetics, when a trait evolves independently in different populations at different times, you see variations in the genetic code. But the researchers found zero variation here. The mutation was identical across the board. The inescapable scientific conclusion is that every single blue-eyed person alive on Earth today, whether it is a Hollywood actor, a nomadic herder in the mountains of Central Asia, or your next-door neighbor, shares one single, common ancestor. Just one. A single individual who lived near the Black Sea 10 millennia ago was the very first person to ever look at the sky with eyes the exact same color. If you are sitting there listening to this with blue eyes, you aren't just sharing a trait with other blue-eyed people. You are participating in a massive, global family reunion tracing back to one ancient mutant. But this incredible discovery immediately presents us with a massive evolutionary puzzle. In the brutal, unforgiving world of ancient history, genetic mutations happen all the time, and they usually disappear almost instantly. If a mutation doesn't offer a massive, immediate survival advantage, like pale skin did for absorbing vitamin D, it usually dies out with the person who carries it, or maybe lasts a generation or two before fading back into the genetic noise. Blue eyes do not offer a survival advantage. In fact, compared to brown eyes, they are technically a disadvantage. Without that thick layer of melanin in the stroma, blue eyes are much more sensitive to light, they are more prone to damage from UV radiation, and they offer zero improvement to visual acuity or hunting prowess. By all the standard rules of natural selection, that one blue-eyed baby born near the Black Sea should have been a brief, unrepeated anomaly. The trait should have vanished as quickly as it appeared. Yet, it didn't vanish. Instead, it exploded. From that one single individual, the blue-eyed gene swept across Europe and eventually the globe like a biological wildfire. If it wasn't helping these ancient humans survive the climate, hunt better, or fight off disease, why on earth did it spread so rapidly? The answer to that question forces us to look away from the harsh mechanics of survival and dive into a much more psychological and, frankly, scandalous side of human evolution. To solve the mystery of why this strange, vulnerable genetic mutation conquered the globe, we have to look past the standard rules of survival and introduce a completely different evolutionary force. We are all familiar with the concept of survival of the fittest, the brutal natural selection where the environment dictates who lives and who dies. But there is a second, equally powerful engine driving evolution: sexual selection. If natural selection is about surviving, sexual selection is entirely about reproducing. You could accurately call it the survival of the sexiest. To understand how powerful this force is, just look at a peacock. A male peacock's massive, wildly colorful tail is heavy. It makes him slow and functions like a neon sign, advertising his location to every predator in the jungle. In terms of basic survival, that tail is a disaster. But he has it because female peacocks find it absolutely irresistible. The reproductive advantage of being so attractive outweighs the survival cost of lugging those feathers. Now, let's apply that to our ancient ancestors living near the Black Sea. Imagine being in that prehistoric tribe. Every person you had ever met in your life had dark brown eyes. Then you meet someone with bright, crystalline blue eyes. It would have been utterly mesmerizing. It was a physical trait so novel and striking that it functioned like human peacock feathers. People with this rare genetic mutation were likely considered highly desirable mates. Because they were sought after, they had more opportunities to reproduce, effectively breeding that rare genetic stutter into a massive booming population. It wasn't the cold or the sun that made blue eyes spread across Europe. It was, quite simply, prehistoric sex appeal. But right as we solve the mystery of how they spread, we crash headfirst into the most massive, mind-bending climax of this entire evolutionary saga. I have been talking all about this blue-eyed mutation, but I have a scientific confession to make. In fact, there is no blue pigment anywhere in the human body. If you are sitting there right now with piercing blue eyes, your irises are not actually blue at all. You are walking around with a brilliantly executed optical illusion. To understand this, we have to look back at the stroma, that front layer of the iris. In a brown eye, as we know, it is packed with dark melanin. But in a blue eye, because of that genetic short circuit we talked about, the stroma is completely empty of pigment. It is basically a translucent layer of tissue. So if it is clear, why does it look blue? It all comes down to a physical phenomenon called Rayleigh scattering. This is the exact same optical trick that makes the sky look blue. The Earth's atmosphere doesn't contain blue gas. It just scatters the light from the sun, and the shorter blue wavelengths bounce around and hit our eyes. Your blue eyes do the exact same thing. When white light enters that clear, empty stroma in your eye, the tissue scatters it. Only the blue wavelengths are reflected back to the observer. You don't have blue eyes. You have clear eyes that are playing a trick with the light. And this phenomenal trick of physics is the master key that unlocks the rest of the human eye color spectrum. What about green eyes, which are the rarest eye color on Earth, found in barely 2% of the global population? Or hazel eyes? Or stormy gray? Just like blue, there is absolutely no green, hazel, or gray pigment in the human eye. They are all just different variations of this exact same light-scattering illusion, mixed with a tiny, microscopic sprinkle of leftover melanin. Think back to your elementary school art class. What happens when you mix yellow and blue? You get green. A green eye is simply an eye where the genetic volume knob wasn't turned completely off, but just dialed down very, very low. The stroma produces a tiny, faint dusting of yellowish pigment called lipochrome. When light hits the eye, the clear tissue scatters the blue light. It mixes with that faint yellow pigment, and the eye appears a vibrant emerald green. Hazel eyes work the exact same way, just with a slightly heavier sprinkle of melanin, usually concentrated around the outer ring of the pupil, giving that shifting, brown-green, multicolored effect. And gray eyes? They are just blue eyes, with an extra layer of collagen protein deposited in the stroma. The collagen makes the tissue slightly thicker and cloudier, so instead of scattering light like a clear blue sky, it scatters light like a heavy, overcast gray sky. So, our entire modern spectrum of eye color, the blues, the greens, the hazels, and the grays, is really just a beautiful accident. It is the result of human populations migrating into the dark, starving for vitamin D, mutating their melanin away, and leaving behind clear tissue that plays tricks with the sun. But this whole time, we have only been talking about Homo sapiens. We weren't the only humans wandering the Ice Age landscapes. Which brings us to one final, lingering mystery. What were our ancient, heavy-browed cousins seeing when they looked at each other? For decades, whenever museums built wax models of Neanderthals, or Hollywood cast them in movies, they were almost always depicted exactly the same way, as dark-haired, dark-skinned, and dark-eyed brutes. It made sense to us at the time, assuming they were just more primitive versions of our earliest African ancestors. But the rapidly advancing science of paleogenetics, extracting and reading ancient DNA from fossilized bone, has completely shattered that stereotype. In the early 2000s, scientists managed to extract genetic material from the remains of Neanderthals found in cold, dark caves in Spain and Italy. When they sequenced the genome, they specifically looked for genes related to pigmentation. What they found was a ghost trait, a specific mutation in a gene called MC1R that causes red hair and pale skin. But here is the absolute kicker. It was a completely different genetic mutation than the one that causes red hair in modern humans today. Mother Nature essentially solved the exact same problem twice. Neanderthals had migrated into the dark, cloudy environments of Europe hundreds of thousands of years before Homo sapiens arrived. They faced the exact same vitamin D crisis in the freezing gloom, and their biology responded the exact same way, by furiously stripping away the melanin. So, if they were evolving pale skin and red hair, did they have blue eyes? The short answer is no. Remember that highly specific HERC2 short circuit we just talked about? That incredibly rare mutation happened near the Black Sea roughly 10,000 years ago. Neanderthals went extinct around 40,000 years ago. They missed the blue-eyed mutation by 30 millennia. However, because they were living in the exact same dim, low UV environment, the pressure on their OCA2 gene, that master volume knob for melanin, was exactly the same. Their bodies were actively dialing down pigment production to survive. While they didn't have the clear, light-scattering blue eyes of modern humans, scientists believe they very likely had shifting, much lighter eye colors. Try to picture a Neanderthal hunter, wrapped in thick animal skins, staring out across a glacial tundra, looking back at you with a piercing, pale amber, or perhaps a haunting, grayish hazel. It was an entirely parallel evolution of eye color, a unique spectrum of prehistoric sight that vanished from the earth forever when they died out. And what about the Denisovans, our mysterious ancient cousins who migrated east into the high altitudes of Asia? The limited DNA we have pulled from tiny bone fragments in Siberian caves suggests they retained the deep, dark melanin of our earliest ancestors, pointing to dark skin, dark hair, and rich brown eyes. So, when our Homo sapiens ancestors were wandering the prehistoric world, they weren't just encountering different species of humans, they were looking into an incredibly diverse array of eyes, each shaped by the brutal demands of entirely different landscapes. When you step back and look at the whole story, the color of your eyes feels like more than a random genetic roll of the dice. It carries traces of our species' past. It is a record written in cells. When you look in the mirror and see dark brown eyes, you are seeing the ancestral pigment that evolved under high UV on the African savanna and helped protect early humans. That common darker pigmentation persisted through much of our species' history and was present for roughly 2 million years. When you see blue, you are seeing a mutation that likely arose in a single ancient ancestor. That lighter, more vulnerable pigment spread through populations in part because of mate choice. When you see green, hazel, or gray, you are seeing the result of different pigment amounts and light scattering in the iris, not a single new pigment. Our eyes have adapted to scorching deserts, frozen tundras, and gloomy ice age forests. But the story of human evolution is never truly finished. As we look to the future and imagine us settling planets with different suns, atmospheres, and radiation levels, you have to wonder how our eyes might adapt to those new conditions. Will a Mars colony or a generation ship in deep space push our biology to produce eye colors or structures we do not yet recognize? Let me know what you think in the comments. What eye color do you have? And which part of its history surprised you the most? If you enjoyed this dive into our past, Please hit like and share the video with a friend who has blue, green, or brown eyes. Subscribe to the channel so you won't miss future videos about human history. Thanks for listening, and I'll see you on the next episode.